Hello everyone, welcome to ECE 6520, lecture number 2. Okay, so before talking about the content today, let's briefly review what we covered in our previous lecture. Okay, so in our first lecture, we covered 4 topics, right? So the first topic is the syllabus, and the second topic is the introduction of information theory, and then we talk about what is information theory, and then lastly we talk about what is information. Lastly, we talk about what is the measure of information, right? How can we measure information? Okay, so as we introduced, so information theory starts from Shannon's seminal paper, A Mathematical Theory of Communication, right? And basically, information theory can provide fundamental answers on the following questions. The first question is, what is information, and how do we measure information, right? So we basically covered these 2 topics in our previous lecture. And in most of the time of this course, we're going to talk about how do we represent information in space and in time. Okay, and basically in space, meaning that we're going to talk about communications, and in time, basically we're going to talk about compressions, right? Okay, so here is an example of a communication system. So this figure basically is from Shannon's original paper, and in this paper, so it gives us, the first application of information theory, which is how to turn information source to message. So that's a compression. And the other thing is how can we transmit information over noisy channel, right? So that is that's the channel coding part of this class, right? So how to turn information source to message. So this is called source coding, okay, or compression. All right, so let's see what is information. So basically, as we introduced in the first class, information is the uncertainty of the outcomes of random experiment, right? So in other words, we think that if the random, the probability of each outcome is more uniform, then we think there is more uncertain, right? And in addition, if we have more outcomes and then the fewer outcomes, of course, under the condition that they are uniformly distributed, then it also means that it's more uncertain, right? More uncertain that it contains more information. All right, so the measure of information is basically so-called entropy, right? And if we consider a discrete random variable x, and the values can be taken in a finite set of calligraphic x, right? And so in this case, so we denote h of x as a entropy, right? And so although we're writing entropy like h of capital X, where x is a random variable, right? But h of x can be considered as a function of the probability mass function, or PMF, right? So in this case, so in most of the classes and also in our book, we just introduce entropy. We just introduce the definition of entropy, or the formula of entropy, right? And later you're going to see that it works extremely well, to quantize, the source coding problem or the channel coding problem. And everything works like magic, right? So when you do a derivation, so the entropy term will come out, right? So kind of like magic, but so in Shannon's original paper, so Shannon didn't define it directly, right? Actually, it was derived from four axioms, right? The first axiom doesn't matter really, right? This is basically give you the unit of entropy, right? And so let's go over it again. So for the first axiom is basically saying that if I have 2 events, right, each of them has half or equal probability, then the entropy is 1, right? This is basically 1 bit. Okay, and we think this this quantity is a monotonic decreasing function of n, so it's kind of intuitive, right? So if more outcomes and each of them has an equal probability, then we think it's more uncertain, right? Therefore, we have more entropy. And so this is a mathematical definition, this assumption, right? So consider h of x is a continuous function of px, so otherwise, so it's hard to, we cannot show it works for the irrational numbers, right? And the last one is the most critical one, right? It's a grouping property. So for this property is like, if we group two event, right? So it's like we consider, so when we do a random experiment, we do that in two steps. The first step is that we're gonna, we see whether the outcome is within one group or in the rest of the outcomes, right? If it's in one group, then we're gonna see which outcome that is, right? This two-step understanding of this random event give it the grouping property, right? So basically, this is the entropy after the grouping, and then we need to add the uncertainty of the outcomes within each group, right? And that will happen with this probability, right? This is kind of intuitive, but so that's the axiom. And based on those four axioms, we can actually show the entropy is defined by this formula, and that is the only possibility of the definition of entropy, right? So we can show, other form doesn't, is not possible, right? This is the only possibility. And so in our class, we just care about the log base 2, right? So the unit of that is bit, right? If it's based on E, then the unit is net, right? There's some other units that we can use in practice as well. For example, if the base is 256, then the unit will be byte, right, instead of bit. But we don't really care about other units. So here in our class, we just care about bits, right? Okay. And maybe sometimes we will use nets as well for the mathematical convenience, right? Because if we take a log, if we take a derivative of a log, so that will be easier. Okay, so yeah, this is a very brief review of our previous lecture. So now let's see what we're going to do today. So in today's lecture, again, we'll focus on the measure of information, right? So like in last class, we just introduced entropy, right? But in this class, we're going to introduce a lot more measures of information, and you'll see the application of it as well in the later part of the class. Okay, so first, we're going to see one simple example of entropy because we have not seen that yet, right? Example of entropy, and then we're going to introduce the concept of self-information. So again, the content is not exactly the same as the book, right? The reason I introduce those concepts is that you'll see, there's a logic of definition for all the concept, right? It's not like we don't have any reason, we just want that. So there's a logic behind it. You're gonna see why. Okay, and so we're gonna briefly talk a few properties of entropy. So we're gonna go back to the properties of entropy in our next class as well, right? But here we can just take a preview of that. And then we're going to talk about joint self-information and joint entropy. Okay, and then we'll talk about conditional self-information and conditional entropy. Yeah, let's put the end later. Conditional self-information, conditional entropy, and also the property of conditional entropy, or so-called chain rule. Okay, and lastly, we'll introduce the concept of mutual information. Okay, so we're not done yet, right? So in our next class, we're going to introduce more measures of information theory. Okay, great. So, yeah. Okay, so let's see the first topic now, examples of entropy. Yeah, just copy the titles here, so make it easier for you to read. Properties of entropy. Okay, so now let's see the first part, which is the examples of entropy. Right, so here, so let's consider a binary entropy function. Okay, so that is the simplest example, and also you can find this example on the book as well. Okay, so we consider a random variable x, so that follows a Bernoulli distribution. So if you have taken 3530, then you must know this distribution, right? So it's called Bernoulli P distribution, and so this basically means that the random variable x will equals to 1 with probability p. So WP means with probability, right? So that's easier to write, and it's 0 with probability 1 minus p, right? It can be vice versa, doesn't matter. Okay, and now let's recall the entropy formula, right? H of, so capital X, right? So here we have to write the random variable x, right? That equals to negative x in all the alphabet, or that's this calligraphic x, and then we have px log 2 px, right? And of course sometimes we can move the negative sign inside, right? So that may be more convenient, so that also equals to px log 2 1 over px, right? And then we can plug everything in, right? We only have two, so in the summation I only have two terms here, right? Because x only has two values, 1 and 0. So now let's see. So basically let's use this formula. Then when px is p, it means that when small x is 1, right? And then have log 2 1 over p, and then the second term is that 1 minus p, then log 2 1 over 1 minus p, right? Okay, so that's basically it, right? So we have a special name for that because it's very typical, and it is the simplest term, simplest example. So that equals to h2p, right? So we just denote that as this. So when you see something like that, so it basically means the binary entropy function. Okay, so now let's plug some explicit value inside. Let's say when p is half, then let's see what the value is. So that equals to basically half log 2 1 over half plus 1 minus half log 2 1 over 1 minus half, right? And then you can see that here is basically log 2 base 2, so that's 1, right? Therefore first term is half, and then the second term, if you compute it, that'll be identical as the first term, so that's half again, and then what we get is basically 1. Right, remember, so the unit now is bit. Okay, so this means that for a Bernoulli source with probability half, then the entropy of this source of this random variable is 1 bit, right? So this bit, is called information bit, right? So the meaning of that is slightly different compared to the bit that we use every day, right? Or the digital bit. Okay, so this basically means the represent the information of a source. right? Okay. In other words, so it doesn't matter what value of p is, right? So in reality, we can always use 1 bit to represent the information, right? Right, we can always use like 1 to represent a 1, 0 to represent a 0, right? So we can always do that, right? But if we want to measure the information, then the value may not be 1 bit, right? For example, let's say when p is, let's consider an extreme case, right, whereas p is 1, right? Then let's see h2 of p equals to 1 log 2 1 over 1 plus 1 minus 1 log 1 over 1 minus 1, right? So clearly the first term is 0, right? Log 1 is basically 0. And then the second term is like 0 multiply log 1 over 0. And, just use your favorite tool, L'Hopital rule or whatever. You consider the limit of this guy, when p goes to 1. Then you'll see this is also 0. Okay? So what does this mean? Right? This basically means that when p is 1, then the entropy is 0. Right? Remember that entropy basically means the uncertainty, right? When p is 1, it means that the source will always take a value of 1, so it will not take the value of 0, right? Therefore, there's no uncertainty. It's extremely certain, right? In this case, entropy is basically 0, so 0 bits, meaning that we don't need any bits to represent the source because it's fixed, right? Certain. Okay, so if we take p for some other value, the value of the entropy can be different, right? So if we draw the h2 of p as a function of p, right, you'll see that. So this is more or less like this. Okay, and here's 0, here's 1, then the peak is at half, and here the value is basically 1. Okay, and you can see that if p take any other value, then the entropy of this, it would be less than 1 bit, right? In other words, it means that we can use less than 1 bit to represent this source, right? We don't always need to use 1 bit to represent the source, although it only takes 2 values. Okay, and very soon we're going to see how we can do that, right? How come we can use some number less than 1 bit to represent a source, right? So basically it's not very magic. So the trick we're going to use later is that we're going to represent a sequence of these random variables instead of just one single this random variable. Okay, but yeah, we're going to go back to this later. Okay, another thing we want to emphasize is that, so that makes sense that the value of the entropy, so it's maximized at here, right? So that should be less than 1, but that is h2 half, right? That makes sense, right? Kind of does, right? Remember the example that we talked about tossing a coin, right? When p is half basically means that the coin is unbiased, right? In this case, when we toss it, we really have any prediction whether it will be a heads or tails, right? Because it's balanced, right? It's unbiased. But if it's not unbiased, it's biased, then we always can guess, with maybe a better chance it'll be heads or tails, right? So it means that the information is less, right? Because we may have a good estimation, but in this case, if p is half, there's really no way to make a good estimation because two events has equal probability, right? It's very uncertain. Okay, so this basically so it means that this point is intuitively it should be intuitively the maximum point. Okay, so let's write it down. So this, in other words, it means that h2p is maximized at p equals 2, half. Okay. Next, let's take a look at the self information. Okay, so let's see the definition of the self information. Again, we consider the random variable x with the PMF px. So this notation basically means that the random variable x has a distribution of has a PMF of px, and clearly x has to be in the finite set or the alphabet. Okay, so we say that if we observe the outcome small x, right? So small x is the outcome or the realization of the random variable x, right? In this case, so then we can define the self-information as the follows. So small I, and here is lowercase x, which is the outcome. So that equals to negative log 1 over px, or here should be px, or that equals to log 2 1 over px, right? So that is the definition of self-information. And so now let's see what is the meaning of it, right? And so basically you can see this is like the one term of definition of entropy, right? Let's recall the definition of entropy is something like that, right? But now we ignore that and then we just take one term out, right? So intuitively this basically means that it's a measure of the uncertainty of one outcome, which is x, right? So the meaning of it is that is the measure, so that measures the uncertainty of one outcome. Okay, clearly that is x, right? So it's just an uncertainty of this outcome, right? And for example, if you see if px extremely small, right, and then this term will be very large, which makes sense, right? If px is small, meaning that it rarely happen, right? If it happen, then we gain lots of information, right? If it never happens, then it happened, so we gain lots of information, right? So one good example is that maybe like the weather prediction or the weather forecast in Los Angeles or here maybe. So because the Los Angeles almost has never rained, right? It rains very little every year, and if the weather prediction predict that it will rain tomorrow, and then if it's correct, then we gain lots of information, right? If it's predict like it's sunshine tomorrow, then we don't gain a lot of information because it's almost sunshine every day, right? So that's some intuitive explanation of that. And now let's say, so if we write small I, but in the parentheses, if I write capital X, right, basically means that we turn from this one outcome to the random variable clearly. So this would be a function of capital X, right? So then that is a random variable. Right? Okay, so for this random variable, so now let's rewrite the entropy of x, see whether we can represent of entropy x as a function of self-information. Okay, so it turns out that we can definitely do that. So let's recall the definition of entropy again. So that is something like this, right? And now we can see this is nothing but the self-information x, right? Therefore, So what we can do is that we can write this as x in calligraphic x, then px ix. Okay, so from this formula, and what do you see? What did you see from here? Okay, it's that the value of ix, and then multiply the probability that it will happen, right? So that is nothing but the definition of the expectation of I capital X. Okay, so entropy can be understood as averaging or the expectation of the self-information, basically, right? So in other words, so self-information is a measure of the uncertainty of one outcome. So the entropy can be understood as, so that measures the uncertainty of all the outcomes, right? Or it's the average of uncertainty of all the outcomes. Okay, so that's some other understanding of entropy, and now we introduce the self-information. Okay, great. So next, let's take a look at the properties of entropy. So here we'll just see some two very simple properties of entropy. So the first one is that, so the entropy, it's always bigger than or equal to 0. Okay, so the proof of that is very easy. Okay, because just from the definition, right, clearly we say h of x, now we can write that as expectation of the self-information, right? So we just need to show that if each self-information is bigger than 0, then h of x would be bigger than or equal to 0, right? So you can see that where the self-information, each term is represented by a of small x, so that equals to this guy, right? Clearly this is bigger than 0, bigger than or equal to 0, because px is between 0 and 1, right? So this is always bigger than or equal to 0, right? Because this term is always, inside is always bigger than or equal to 1, right? Okay, it's very easy. And the second property might be more interesting. So this property is that, so h of x is always less than or equal to log 2 of x. Right, remember that this basically is the alphabet of the random variable x, or the finite set, right, of all the outcomes of the random variable x, right? So, and this bar here, or this means the cardinality, right? This basically means that h of x is always less than log base 2 of the cardinality of the finite set, right? And note that here the equality sign can be held, right? So the equality sign can be true, right? Now can you think why it can be true? So did you see anything like that before, right? For example, how about here, right? This is nothing but what? Equals to log 2, right? Where 2, right, that's basically equals to the cardinality of 2, right? Because now x can only take value of 0 or 1, right? Therefore, so this basically is an equal sign here, okay? So in this case, so okay, so now can you think what is the condition of the equality that'll hold, right? Okay, so basically it means that the equality will hold if and only if, right? So there's two directions, if and only if. So the random variable x will follow a uniform distribution, right? Which means that, so for each value of x, so that'll be taken with a probability of 1 over n, where n is basically this value, right? So x is uniform, okay, over this alphabet x. Okay, so So this is not very hard to prove, but it's not extremely straightforward either. So we're gonna use a very famous inequality that we're gonna learn later in the next class to show it, right? So now, just remember this. So we will prove it later in the next class. Okay. Next, let's take a look at the second topic of today's lecture, so which is the joint self-information and joint entropy. Okay, so from now on, we will always introduce the version of the self-information first, and then we introduce the corresponding entropy term, right? Because as we see before, the entropy is nothing but the expectation of the self-information. Okay, so this concept for the joint stuff is pretty straightforward. So the reason is as follows. So joint here basically means that we consider more than one random variable. Okay, so here let's consider discrete random variables. Okay, so if you forgot, the discrete here basically means that the calligraphic x is finite, right? So and it only takes discrete values instead of continuous values, right? So we consider, let's say, two random variables, x and y, and we write in this way. Okay, then we assume that x and y follow a distribution px and y, right, where x is in some alphabet and y is also in some alphabet. Okay, so this pxy is nothing but the PMF, okay, of this two random variable, right? It's a joint distribution, right? So the reason I'm saying, so this definition is straightforward, is that so we can consider this xy as a whole, right? As basically we consider this as a single vector valued random variable. Okay, so RV means random variable. Okay, so in this case, so we can basically copy and paste the definition we defined before, right? For example, the joint self-information is defined as follows. We write I, small x and small y, so that equals to log base 2 1 over px and y, right? The meaning of this is identical as before, right? So the only difference now is that now the outcome is a pair instead of a single value. Okay, so this is basically the joint self-information. Therefore, correspondingly, we can define the joint entropy, right? Joint entropy of these two random variable would be, so we denote that as hxy, right? Similar as before, right? That should be nothing but the expectation of I, capital X, capital Y, because those are the random variables, right? So if we write this out, so that basically equals to expectation of, we need to do this expectations over both x and y, right? Remember, we consider x and y as a single random variable now. So x in x, y in y. Yeah, there's a typo here, right? So y should be in y. Okay, and then we have a negative sign, or let's say we put 1 over px y, and then we need to let's write the probability first, right? It's pxy and then log 2 1 over pxy. Okay, or we can take this 1 over out, right? So that equals to negative right? So this is the definition of the joint entropy, and clearly the joint entropy is also bigger than or equal to 0. Okay, so yeah, this is basically joint entropy, and from here we can basically generalize it to a number of random variables, right? So it doesn't matter. So this can be generalized to any number of any finite number of random variables. Okay, good. So next, let's consider the third topic of this class, so which is conditional self-information and the conditional entropy. Okay, so here again we consider the two random variables. Consider the random variables x and y again. So we assume that they follow a PMF like that, and for x in x, y in y. Okay, and then so we define the conditional probability mass function. Right, you should have seen this in 3530, right? So that is basically using the Bayes rule, right? You have px given y equals to pxy over py, right? This probability basically means that, so if you observe or given the outcome y, then what is the probability that x equals to the small x? Right, it's a conditional probability, and from here we basically can define the conditional self-information, right? Let's say given the realizations, let's write it more clear. Okay. Realizations basically means outcomes, right? We use these two words interchangeably. Let's say the realizations is x, y. They're all lowercase, okay? Then we can define the conditional self-information as, right? So this basically means that if we have observation of y, and then what is uncertainty of x, right? That means conditional. Okay, great. So we write this as I x given y equals to log to 1 over p x given y. You can see that is almost identical as the definition before, right? So before we defined this as something like that, or if there's only one x, then we just define this 1 over px, right? But now it's a condition on y, right? Okay, so yeah, let's mark it. So it's called the conditional self-information, and this is given by this formula. Okay, good. So okay, so as we said before, the meaning of it is nothing but the uncertainty of the outcome x given the outcome y, right? We know, we observe y, then what is the uncertainty of x? Okay, great. So now, based on that, we can define the conditional entropy, right? So we have to be a little bit careful here, right? Because we have two random variables, right? Let's see how we can introduce the concept of conditional entropy, right? So now let's fix y, right? Let's consider that still we're given the realization y. Okay, this is lowercase y, so it's just a number. So if that happened, then we can actually compute the average of this guy where x is the random variable, right? So it means that we can define, let's say we could compute this guy, expectation of I, where capital X, so X can be considered as a random variable, and then given small y, right? Which means that we observe y happened, okay? So give a symbol to this guy. So this is nothing but the entropy of X given y equals to y, right? Because that's a realization, right? Okay, so now we can write it down, right? Because we know the formula of this guy, and then we just take an average of this, right? So now let's see, this equals to nothing but, so remember now y is fixed, right? So x is a random variable, therefore the expectation will be taken over capital X, right? This is expectation is over capital X. So this basically means that, so remember y happened, right? So it cannot be, so the probability we multiply here has to be x given y, because y is happened, right? So x given y, and then log 2 1 over px given y, right? We just copy and paste the definition of conditional self-information here, okay? And then, so this is basically the formula to compute this guy, okay? So, okay, so are we done yet? Right now, really, right? This is a function of y, right? So before, when we think about entropy, is the averaging concept, right? So it's not a function of each realizations, right? So the natural thing to do here is nothing but, how about we take another expectation over y here, all right? So what we're going to do now is that, okay, so now we're gonna take the expectation. So we're gonna take expectation of this guy again, but here, instead of given y, so it's a given the random variable y. It's just another expectation of this guy, but we've taken that over y, right? So for simplicity, we just write one single expectation here, but you know, that's two steps, right? The first one is to take the expectation of x given y, and then we take the expectation of y, right? Okay, so we can write this as this guy, okay? And then, so that can be equals to, so now we just compute it, right? So basically, so we need to compute this guy and then average over y, right? So we have y here, and then we need to use py multiply this guy, right? Okay, multiply x px given y, right? So now let's do some rearranging, right? This guy equals 2, so we take this 2 sum in front. Let's say we sum over x first and then sum over y, so it's all finite, right? So we can do this changing easily. We just multiply this inside, right? Then we have, so note that, so this py multiply px given y equals to what? See here, right? Because of the Bayesian rule, px given y multiply py, that'll be nothing but pxy, right? So we can write pxy here. Okay, then log 2 1 over pxy, and that's it, right? We're done. Okay, so in other words, right, so we can also see this guy is nothing but, so here, so this is basically the average over x and y, right? We can understand this as what? Expectation of nothing but 1 over log 2 1 over px given y, right? Where this guy yeah, it's not very good to write in this way, right? So yeah, if we write in this way, so basically it will have to be, yeah, no, here has to be something like this, right? Capital. Okay. So basically what I'm saying is that this is nothing but this, right? So this is the average over both x and y on the self information. Okay, so now we'll give a new name for that. So this is called hx given y. Both x and y here are random variables, right? So this is called the conditional entropy, right? So conditional entropy is a concept that will take the average on both x and y. Okay. All right. So it's like it's an uncertainty, the average uncertainty that observe the random variable y, and then what is the uncertainty for x? Okay. Okay. So again, so this is also entropy, right? So given this format, you'll see, so we can see immediately that this guy is also bigger than or equal to 0. All right. Okay. So yeah, this is the conditional entropy. So now we have introduced entropy, joint entropy, and the conditional entropy, right? Just keep tracking those concepts. So we're gonna introduce a lot more. All right. So okay, so now let's do some manipulation of this conditional entropy, right? So we know that this guy equals to, let's write down the definition again, x in x, y in y, pxy log 2 1 over px given y, right? So now let's again use the BS rule to break this term into two terms. Okay, so what we're gonna do is as follows. Pxy log what? So it should be py over pxy. Okay, so here is the Bayes rule, right? Bayes rule. Okay, and then yeah, because we have a log here, right? Log and inside is a division, so we can break this into two terms. Okay, let's do that. So that is pxy log py, then minus again pxy log pxy. Okay, so what's that? We have seen that before, right? Remember? So when we talk about joint entropy, so we see something like that, right? Okay, or this, right? Therefore, we can actually, we need to include in the minus sign, right? So this term equals to nothing but the joint entropy. Okay, so now let's see what this guy is, right? Let's see. So this guy, so now here is a summation over both x and y, right? But here is just y. So if we take this over x, and then we get the marginal distribution or the marginal PMF, right? So let's see, if we compute the marginal distribution, we move this inside, and then we can get, so this, so we'll have py here only, right? X will be gone if we take the summation over x, and then is the log py plus hx and y, right? And clearly this looks very similar. Yeah, if I miss the 2 here, I mean all the log will be based on 2, right? So understand that. Okay, so this is almost the definition of entropy, but what we miss is a negative sign here, right? So therefore, we need to take a negative sign here, and then take another negative sign out, right? And this guy, clearly that is hy. Okay, so in other words, that will equals to hx of y minus hy. Okay, so now let's write it more clearly. So it's hx, or we can move it a little bit. So it's hxy equals to hy plus hx given y. So this is one important identity that we're gonna use all the time in this class, right? And you can see this is not very hard to remember, right? It's almost like the Bayesian rule, right? So in probability, so pxy equals to py multiply px given y. So here just a plus, right? Because we derive it from the Bayesian rule, right? It should be similar. So, but in information theory, we have another name for it, right? It's called chain rule. So it's a chain rule of entropy, and we're gonna see in our next class. So we have the chain rule for other measures of information as well. Okay, so this is a chain rule for entropy. Okay, so actually now we only consider two random variables, right? So actually we can generalize it. Okay, so it's very easy to generalize it. Okay, so we're going to introduce more notations here that we're going to use all the time. So we let x, so n, right? X is a random variable, so if we put a small n here, so this means a random vector, okay, that has x1, x2, and so on until xn. So that is a random vector. So if we want to compute the entropy of the random vector, right? So this is basically the joint entropy of x1, x2, and so on, right? Okay, so based on the chain rule, again, so that's from the Bayesian rule, Bayes rule, right? So that equals to nothing but a h of x1 plus h of x2 given x1 plus h of x3 given x1, x2, and so on until h, the last term is xn given everything before, right? So we can write it in a more concise way, so which is that, so I from 1 till n h xi given x1 till xi minus 1, right? Or we can write this as h xi given xi minus 1, right? According to our notation here. Okay, so this is a generalization of the chain rule of entropy. Okay, very good. So now I have a few remarks to make for the conditional entropy. So know that. So maybe this is obvious, but right, just be careful. So in general, h of y given x and h of x given y. So is there any relationship between these two quantity? Right, there's no, right? Usually those two are not equal to each other, right? Just be careful. And but the other thing may be true, right? So how about I give you another two quantity, so which is hy minus hy given x, another one is hx given hx minus hx given y, right? How about these two quantity, right? It's also kind of like symmetric. Yeah, maybe. Okay, so are they equal? Right, they should be equal, right? If how to prove that is very easy. You just move this here and move this here, and then both sides will be equals to the joint entropy. It's very easy to prove, but be careful on that. And the other thing I want to emphasize is that, yeah, let's say here is small 1, small 2. The other thing I want to emphasize is that, so how about h of x given x, right? So intuitively, this basically means that if I know x, then what is the uncertainty of x? Right, kind of a very naive question, right? If I know x, then there should be no uncertainty of x, right? Therefore, the uncertainty should be 0, right? So it's kind of, again, easy to prove. So that equals to, as we said, should be I, expectation of I x given x. We just have one random variable here, right? And clearly, I x given x, that is always 0, right? Remember that equals to nothing but 2 over px given x. Clearly, if we know x, probability of x equals to x, it will be 1, right? So that is trivially 0. Okay, so this is the conditional entropy. Okay, so next, let me introduce the next concept. So which is the fourth topic of our class. Let's see what kind of number I used before. 3. Okay, should be correct. So the fourth topic of our class, so that is mutual information. Right, let's see what does that mean. Yeah, we're kind of almost finished the entropy part. There's only one more concept left. But now, so we start introducing the mutual information like measure of information. Okay, so let's see what do we mean by mutual information. And again, we consider a pair of random variable, right? The distribution or the PMF will look like this. Okay, so now let's see. So let's do the following, right? Let's say we observe the outcome of x, right? Let's say we observe x, right? So that's a realization. So we know x happened, right? Okay, so in this case, so let's consider the following two observation, right? So let's say if we say we knowing nothing about y. Okay, let's say we know, maybe, yeah, consider this case, this scenario, knowing nothing about y, then what is the uncertainty of x? Okay, right? So because we observe x, right? So this basically means that we need to use the self-information to represent this event, right, or this experiment, right? If we know, we should know nothing about y, right? It should be just this. Okay, so so because we know nothing about y, right? So now let's see, on contrary, let's say if we observe y, right? We know y is y. Okay, let's say this is known, right? And then what is the uncertainty of x? Right, that will be I x given y, right? This is the uncertainty of x. Okay, so now we have two scenarios. One is that we know y, the other is we don't know y, right? So it's like this is the the total uncertainty of the symbol x, and now we have the uncertainty that given y, right? So it's like, so now I ask, so what do you gain in terms of information if we observe y, right? In other words, so what is the reduction of the uncertainty if we observe y for the outcome x? Okay, it means that we need to use the first term minus the second term, right? The formula looks ugly, but it's this one minus that, right? That is the reduction of the uncertainty if we observe y, but only for the single outcome x, right? So we give a notation for that. This is denoted as I small x semicolon y. This is important. It's not a comma, right? The semicolon. Okay, so this is one formula, although it looks long. Okay, and so we give a special name for this. Can you tell me what that is? Right, normally, right, it's a joint information, joint self-information, right? Conditional entropy, joint entropy, joint self-information, right? Conditional entropy, conditional self-information, right? Mutual information, that will be self-mutual information, right? So yeah, we call this as self-mutual information. Okay, so as we explained before, the intuitive meaning of this is that, let's write it in the parentheses. So this basically means that the reduction of uncertainty of outcome x, given the fact that, let's say, if y is known. Okay, great. So now let's write the formula of it. So that equals to the self-mutual information equals to Ix minus Ix given y. So that equals to, let's use the definition of the self-information and the conditional self-information. So that is log 2 1 over px minus log 2 1 over px given y. Right, okay, good. All right, so now we can see this guy y equals 2. So now again use the Bayes rule to expand this term as two terms, py over pxy, right? And then so it's a log, right? So that equals to this guy divided by this guy, right? What that equals to? That equals to, right, if we use this guy divided by this guy, so the pxy will becomes upstairs, and then downstairs will be px and py. Okay, great. All right, so this is basically the formula or definition of the self-mutual information, right? That equals to that. So from now on, we're gonna do something very similar as we do before. Okay, so before doing that, doing some averaging, of course. Before doing that, so let's emphasize one important property of the self-mutual information, which is the commutative property, right? Ixy will equals to y semicolon x, right? So you can double check. It's very easy to prove this is true, right? Just write down two definitions and you'll see that they will be identical. Okay, very good. So okay, so now we're gonna do something very similar as what we have done before, right? We have two random variables now. So basically, we're going to do the average over x and then trying to do the average of y and see what happened, right? Okay, so yeah, let's see. As if we make x as a random variable, then we can do this expectation over x, of course, over x, right? So that equals to what? So x in the alphabet of x, px given y, I x given y, right? So now, so note that here is we're given the realization of y, right? Here we should write the conditional entropy, conditional probability, right? Okay, so here is that x given y, and then the self mutual information. Yes, here's a typo, right? Semicolon. Okay, be careful, right? Very easy to make mistake here. Okay, so and then we have this formula, right? So we have special notation of it. So we're gonna write this as capital Y I, and then x semicolon y equals to y. Okay, and then we're gonna do the averaging over y, right? So now let's do this averaging over y. Then we can write down this is expectation. So it's another expectation over y on this guy, right? Therefore, you can write things together. That is x, y, right? Both capital, right? That equals to. So now we just need to do another average on y over y of this quantity, right? So that is y in y, p y, x in x, px given y log 2. Oh, here I made a mistake, right? So be careful. Px py over px py. Okay, good. Okay, so after this, now similar as before, let's do some rearranging here, right? So we're gonna write this as a summation over x, and then summation over y. So now here py multiply px given y, so that's the base rule again, right? So that's pxy, and then we have log 2 pxy over px py. Okay, good. All right, so we're done, right? So this is called mutual information. Okay, we're gonna give a notation for that. It's capital I, capital X, semicolon Y. Okay, so this is called mutual information. Okay. Okay, great. So this is the definition of the mutual information, right? Maybe let's mark it, very important. This is the mutual information. Okay, entropy and the mutual information might be the most two important measure of in information theory, right? And so let's recall. So entropy basically means the uncertainty of a source or uncertainty of a random variable x. Okay, but mutual information, as we said before, so this basically means that the reduction of the uncertainty of x given y, right? So it's like if we observe y, then what is the uncertainty left for x, right? So the reduction yeah, maybe what I said is not correct, right? It's a reduction of the uncertainty, right? So it's the original uncertainty of x, and then minus the left uncertainty of x given y, right? It's a reduction of the uncertainty of x when we observe y. Okay, so hopefully I'm clear enough, right? In other words, we can see this basically maybe more clearly from formula. So let's recall. So now this guy is nothing but the expectation of I x given y, right? And if we write the definition of ix given y is ix minus ix given y, right? So now let's break this, right? The expectation. So we break this as two terms, right? Minus given y, and both of them are something that we have defined before, right? So if you forget, just go back. The first term is nothing but the entropy of x, and then the second term is nothing but the conditional entropy, right? Therefore, you can see that the mutual information basically means that the uncertainty of x and the minus the uncertainty of x given y, right? It means that the reduction of the uncertainty if we observe y, right? Of course, in the average sense. Okay, so this formula is also very important formula that everybody should be extremely familiar with. Okay, all right, so now let's try to see some other relationship between mutual information and entropy. Okay, great. So now let's write this down again. We just derived this equals to that. So you can almost understand, consider this as a definition for mutual information, because that is a formula that we're going to use all the time. Okay, so let's do some derivation here. So remember, so we give a formula for h x given y, right? Let's see whether we can find it or not. Yeah, here, right? So we see the mutual information, the conditional information, conditional entropy x given y will be nothing but this guy minus this guy, right? This guy equals to this guy minus this guy, right? So let's use this formula here. Okay. So hx given y, so that equals to hxy minus hy. Okay, so now so that will be equals to hx plus hy minus hxy. Okay, so this is basically another formula for mutual information, right? Okay, which might be important. Okay, and next, if we keep manipulating it, so we can see that. So so let's combine this term, the first term, and the third term, right? We have hy minus hxy minus hx. So what is that? Right? This is nothing but the conditional entropy of y given x. Okay. Again, so this is equal to that. So this is, therefore we can see that. Well, yeah, let's keep the notation here. So for this guy, we can represent this as this, right? But now we kind of exchange the order of x and y, right? Therefore, we know this guy will still equals to x, y, because we derive from here, right? And also from here, we can conclude that that also equals to mutual information between y and x, right? So the mutual information is commutative, right? So we also, yeah, remember that I also say the self-entropy is commutative as well, right? So they're sort of the same thing. All right, okay. Okay, great. So maybe let's write it more explicitly, right? So now we have a few formulas for mutual information that we can use, right? Normally in our proof, these two expressions are extremely important. So we're gonna use, most likely we're gonna use both of them for, the proofs later that we're gonna do. All right. Okay. So one more thing that I want to emphasize is that let's say what happened if x and y are independent, right? Let's say if x and y, these two random variables, are independent, then what do you think for their mutual information, right? So what do you think? Let's compute it, right? So that equals to, again, as we said before, so we can almost use this as a definition for mutual information, right? So this basically means that hx minus hx given y, right? If x and y are independent, what do you think this term will equals to? Right? Independent means that all the probability term, the given doesn't matter, right? So this will equals to basically h of x. Right? In other words, we say if x and y are statistically independent, by observing y, we cannot gain any information for x. Right? It's like we didn't observe anything, right? Therefore, this guy will be equal to 0. Okay, so if x and y are independent, the mutual information will be 0. All right, okay, and we see, so let's see this formula again, right? This mutual information equals to hx plus hy minus hxy. So from here, what can you sort of think about, right? Do you remember? So do you remember the Venn diagram, right? Something like this. So if we draw a circle, okay, and then we draw another circle, right? And what is the value of the middle part? Right? The value of the middle part is like the area of this circle plus the area of this circle and minus the area of the entire thing, which is something like this, right? Therefore, we can represent the relationship between the entropy and the mutual information using exactly this Venn diagram. Okay? So basically it means that the first circle represents h of x, the second circle represents of hy, and the middle part is nothing but the mutual information between x and y, right? And the whole thing is what? The whole thing is something minus here, right? So the whole thing is the joint entropy, okay? And also you can see that. So what is this part? Right, this part without this, right? So this part is nothing but hx given y, right? Because so this part is the mutual information is nothing but hx minus this, right? Therefore, for this part is nothing but hy given x, right? You can use this Venn diagram to represent almost all the quantity that we have learned so far. Okay, very good. Okay, so now what we have defined here is just mutual information, right? So now we have entropy of mutual information, and we have conditional entropy. So do we have a conditional mutual information, right? So the next we're going to talk about the conditional mutual information. Okay, so the definition here is it's very similar as before, right? Instead of 2 random variables, now we have 3 random variables, right? So consider the random variable x, y, and z, and their distribution function, or the PMF, is px, y, and z. Okay, and similar as before, so we can define the conditional mutual information, the conditional self mutual information, which is I x semicolon y given z, right? It means that that the definition of this is identical as before. The only difference is that we're gonna given every probability on z. Okay, and so this is defined as I x given z minus I x given y and z, right? And from here we can define again. So now we have to do 3 steps instead of 2 steps for the averaging, right? The first step, let's say we take the average over y, right? We can have, I mean, it doesn't matter, right? X and y, they're all identical. We can take an average of y and have something like this, right? So that's the average of this guy over y, right? So it's like small x, capital Y, and then z, right? And then after that, we can take the average on x, right? We can have this, and given z equals to z, so that is the expectation here of I. We have capital X, capital Y given small z. Okay. And then finally we can take the average over z, right? Because we don't want this is only a realization. So then we have notation wise, that would be something like this. And this is defined as expectation on all of the x, y, and z. X, y given z, right? So this is the conditional mutual information. All right. Okay, great. So yeah, that'll be the end of today's class, right? So today's class we introduced the joint entropy and the corresponding joint self mutual information, and then we introduced conditional entropy, conditional self information, and then conditional entropy, conditional self information, and then mutual information, conditional self mutual information, and lastly is a conditional mutual information and conditional self mutual information, right? So they're related, and check this very carefully. And in our next class, so we're gonna continue talking about this and some other relevant measure of information, and then we're gonna see some common important inequalities that we'll use all the time in information theory. All right. Okay, that's it for today. So please let me know if you have any questions or comments. So otherwise, please stay safe and healthy. I'll see you next time. Bye.